Hello, everyone, and welcome to our live session for today, October 22nd. My name is Matthew. I am one of the course instructors for our online classes, and I do a lot of the behind-the-scenes stuff here at the Teach Astronomy headquarters. Thank you for joining us today. We are excited to have you here. I'm going to go over sort of the structure of how these live sessions run, and then we will get straight into your questions for today. For those of you who have found us through our classes, we have online classes offered through Udemy and Coursera. So if you are joining us not from those courses, you should go check those out. I posted a link in the chat. For those of you who are here from our courses, welcome. We're excited to have you here. The way this works is you post your questions in the chat. I will go through those questions. I will pick them out. And I will relay them to Chris, make sure that they're as clear as possible. And if I have a question, I will try and prompt you in the chat for more information or for clarification. We try to generally go in the order that questions are asked, but we do jump around a bit to try and give everybody a chance to have a question of theirs chosen and to cover a variety of topics. We need you to only ask your question once. I promise we see everything that comes through the chat. If we haven't gotten to it yet, then you'll just have to wait your turn. Also, I can't get to every question. Again, sometimes we have had a question that gets brought up a lot. We get a lot of black hole questions. We get a lot of how do I get into astronomy as a profession questions. So we don't select those every live session. If you'd like to email your question instead of asking live in the chat, again, check the chat and you can see the email address. Make sure you like, subscribe, follow our channel so that you can find out about upcoming live sessions. We also have a listserv for Google, so check that out. And subscribe to our Google Calendar so you can find out about upcoming live sessions. I think that's all of the business announcements. Chris, I will let you just welcome everyone, and then we will get started with your questions.
Okay, welcome everyone. However you encountered our live session, either one of our MOOCs or just discovered us by some other means. Everyone is welcome here, and we have a big international audience, actually. And the floor is open for questions on any topic in astronomy.
Excellent. Thank you very much. All right, we are going to get right into our live participant questions. So the first question is from one of our live participants. Let's see here. We've got Terrence, who loves to join our live sessions. Thank you. Welcome back. The first question is astrobiology a real college course? How can that be since there haven't been any discoveries of extraterrestrial life?
Two good questions. Yes, it is an actual college course. I think it only is offered in places where there's a very strong astronomy program and an astrobiology research group typically, because you need that expertise to teach astrobiology. It's very interdisciplinary, involves biology, astronomy, of course, planetary science, physics, and chemistry as well. So yes, astrobiology is a real course. It tends to be not offered at a lower undergraduate level, although we have a tier 2 or sort of general education course called Life in the Universe. It's very popular. It's actually more popular now than our introductory astronomy course. So it's offered at maybe sophomore or junior or senior level in other departments too. And then at the graduate level, definitely astrobiology is a course. And we have a couple of astrobiology courses in our graduate program. It is a subject, even though we haven't discovered life beyond Earth, because the overarching issue of life in the universe involves several things. It, of course, involves discovering life elsewhere, if it exists. We don't know that yet. But it also involves understanding the history of life on Earth and understanding what are the conditions by which biology emerges on a terrestrial planet. That's happened here, but we don't know if it happened anywhere else. So a significant part of astrobiology is the inward-looking part about life and how it emerges and evolves on this planet. And then, of course, because of the great success with exoplanets, the table is set, if you like, for the discovery of life beyond Earth, because we have thousands, over 7,000 confirmed exoplanets. Hundreds of those are Earth-like in mass or size and could host liquid water, and so are habitable, in a simple definition of that term. And so these are the other bit of astrobiology involves finding the sites for life, the plausible sites for life, and we've had enormous success with that. So that's where the meat of astrobiology comes from, even though we still don't know of life anywhere else.
The next question is from Sonakshi, who asks, what are the current updates, or do you have any current updates on the Europa Clipper mission? So maybe you can explain what the Europa Clipper mission is and what's the status.
Yeah, the Europa Clipper mission is a very important outer solar system mission to go actually to several of the potentially habitable moons of Jupiter, the big moons of Jupiter. Ganymede is another very important target, which is an even bigger moon than Europa. Europa is the water world, and so it's the centerpiece, if you like, of the Europa mission. But when you send a space probe 1 billion miles from the Earth, you want to get as much out of it as you can, and so it's going to spend time in the Jovian system exploring several moons. But its biggest target and its most frequent flybys and inspections will be of Europa, the watery moon of Jupiter, one of the Galilean moons discovered by Galileo 400 years ago. It will not land on the surface, and it will not do formal life detection experiments, but it has very sophisticated gas chromatographs and mass spectrometers to sniff molecules in the European environment, and I think potentially splash off some of the material of the European icy surface and then sniff that or pass through that material in a subsequent orbit. It's very exciting. In the same way that the Cassini sampled the icy jets, the geysers of Enceladus. And so it's going to look for life ingredients, the ingredients for life. Are the ingredients for life there? And in particular, what is the nature of the sub-ice oceans on Europa? How saline? What is the pH of that water? What are the nutrients or other ingredients there? And so is that an ocean or water body that could potentially host life? So it's an important mission. It's on its way. After many delays, I think the launch date in the end was multiply delayed. It was problems with NASA's contributions to the project because NASA's funding has been so tight, not just under a government shutdown and recently, but over the last few years. And it will take years to get to Europa, and I think the main data from that mission won't really be in until the end of the decade.
Excellent. Thank you very much. The next question is from Natalie Walker, who asks, hi, Professor Impey. Assuming funding, how ready are we for an exoplanet mission in terms of technology? How long would it take us to prepare if we're not yet ready?
Well, there are missions on the drawing board. I mean, the enormous success of the Kepler mission, which is just a 1-meter telescope, did most of its work over a decade ago, but found thousands, literally thousands of exoplanets. About half of the total known were found through that one mission. There have been follow-up missions. There was a precursor mission, Corot, a European mission, a smaller telescope, didn't find as many exoplanets. And so the current hope is for a true life sensing mission, which will home in on the Earth-like and most habitable exoplanets of the thousands we know. Now, that mission started off as being called the TPF, Terrestrial Planet Finder, and the mission concept, design, and name has morphed several times, so I'm not even sure it's in its final form now. It's an ambitious mission. It has a coronagraph. It has the ability, and we'll also probably have a starshade, which is a free-floating device entirely designed to suppress the light from a star so that we can see the very faint reflected light of an exoplanet and study that to look for signs of life through spectroscopy. So it's a very ambitious mission, multi-billion-dollar mission, no doubt. Is not funded. It's only funded at a level of design studies. Many major astrobiologists are involved in the team behind it, and they clearly hope that it will happen and be the next frontier mission of astrobiology in the next decade.
The next question is from Saad, who's on with us live. Hello, Professor. When astronauts look at the stars with the naked eye in space, do you think that the stars appear brighter, clearer, and more numerous than when we see them from Earth on a clear night? Thanks.
It's a good question, and the basic answer is yes, with a caveat. I mean, yes, because the environment of the International Space Station at 350 miles roughly above the Earth is incredibly dark. So when you're looking at that backdrop of sky, the sky is just much darker than even a clear mountaintop and a moonless sky you could have on the Earth, because the Earth's atmosphere has a faint glow, air glow, and that's significant. So it's a much darker sky in space. So looking out from the space station, yes, in principle, you can and should see more stars. Now, in practice, that benefit is offset by two things. It's offset by the fact that you're looking through very thick, multi-plated windows, which have some internal reflections and don't completely and cleanly transmit all the light that comes into them. So there's a little loss there. And the other loss is just, of course, that you're in space where there is also a local environment of the International Space Station, which is not perfect. So the International Space Station is not a totally clean environment. It outgasses from various plastic and metal surfaces. There's sort of mild amounts of debris surrounding the space station at any given time. So it's not a perfectly clean or pristine environment, but generally, yes, the sky and the stars would look better and darker, and there'd be more of them from space.
The next question is from Dave McKenzie, who sent an email. Have astronomers ever observed a supernova completely from its collapse through the explosion?
Astronomers don't get to anticipate a supernova. So the basic answer to the question is no, because you would have to know with some precision when a star was about to undergo core collapse at the end of its fusion stages. And although we can diagnose from observing massive stars near the end of their lives that they are indeed in the later stages of fusion, and those stages move very quickly. The final stage of fusion up to iron, for example, in a very massive star, only takes about a day. It's really fast. It's a crescendo of activity going up the fusion chain. But there's no signal from a star of what part of the late part of its life it's in. And so you don't get that kind of heads up. So basically, we only see with prompt observations, that is because we're monitoring the sky, we see the brightening of a star caused by the fireball, caused by the core collapse, and then the explosion that follows, heating gas into a plasma of billions of degrees and creating heavy elements. And so a number of supernovae have been caught that way at the moment the explosion happened, and then followed for weeks and months afterwards as they faded. But we've never actually observed the run-up to a supernova.
The next question is from Lawrence K., who's on with us live. Regarding black holes, I'm kind of unclear on how they lose mass or energy. Do the infalling virtual particles only have negative energy? And is Hawking radiation only observable at a distance, not at the event horizon?
So the issue of Hawking radiation, or the mechanism of Hawking radiation, which is the basis for both the fact that black holes have a very low temperature and are emitting radiation, and the fact that they are slowly evaporating, is because the vacuum of space has the potential to create particle and antiparticle pairs. So that is literally a property of the vacuum. It doesn't matter whether there's a black hole nearby or not. So particle-antiparticle pairs are coming in and out of existence all the time in space and disappearing very quickly, tiny fractions of a second. Now, when that process happens near the event horizon, at the event horizon of a black hole, there's a finite probability that one of the particle or antiparticles in the pair will go behind the event horizon and essentially be lost to the universe. And so if that is an antiparticle, it doesn't matter whether it's a particle or an antiparticle, it has mass. And so if the particle goes out from the event pair, it will just be the loss of that particle. If an antiparticle goes out, it will react with a particle in the environment of the black hole and create radiation. So either way, you get the loss of a particle or radiation. And where does that essentially is borrowed from the vacuum of space, but it is a net loss to the black hole. So black hole radiation and particle loss do create the evaporation that leads to the fact that black holes are not eternal.
The next question is from Jane, who is on with us live. If you had to guess, Professor Impey, what are the odds of finding evidence of life on other planets in your lifetime?
I hope to live another 10, 15, 20 years. Who knows? I'm almost 70 now. But I think very high. I mean, I think they're high within the next 5 to 10 years. I'm pretty confident of that. And that's because we have so many Earth-like exoplanets discovered, hundreds of them. And our techniques are progressing, altering the atmospheres, as happened on the Earth, to create the oxygen we breathe. Those experiments can be done almost as soon as those telescopes are commissioned. And the extremely large telescope of the Europeans soon after that, and the Californians have a telescope that may take a little longer than that. All three telescopes can do this experiment. So by the mid-2030s, we'll have 3 frontier facilities all looking very hard at Earth-like planets that are habitable. They're in the right mass and size range, and they have the right temperature relative to their star, and they have all the chemical ingredients for life. So there's no reason there shouldn't be life on any of them. There may not be, and that would be a null result and telling us something about the universe.
The next question is from Layla, who sent an email. Why do we use Roman names for most objects in our solar system? Maybe you can talk a little bit more generally about how objects are named.
Sure. So the naming of the planets in our solar system, those are the best examples to take, because remember that the five objects visible to the naked eye, the astronomical objects visible to the naked eye, of course, are the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. So the Earth, the Moon, and the Sun, and then 5 planets. Those 5 planets have historically been named by the earliest civilizations that were interested in them, and all those 5 planets named originally had Greek names, and then Roman names followed. So some people know them by their Greek names, some by their Roman names. The Romans came after the Greeks in general, so the Roman names and the dominance of the Roman Empire sort of means that we tend to use the Roman names for these planets. And so Mercury, Venus, Mars, Jupiter, and Saturn, those are Roman gods. And that's a historical naming convention that goes back hundreds of years. Galileo tried to name the 4 moons he discovered with the early telescope after his patron, essentially, the Duke of Medici. He called them the Medici objects, 1, 2, 3, and 4. And that got overruled by professional astronomers when they started naming things. And so the moons of Jupiter and Saturn were also named after gods, typically Roman gods, but also Greek gods. And so through the 19th century, large objects were named after mythological figures. The first asteroid, Ceres, another Roman mythical figure. And they spread the cultures around. So in more recent times, and with more objects found, Saturn and Jupiter have over 100 moons each, and they all get names. You tend to run out of the major gods, of course. And so the major gods have all been named. Their names have all been used. And you're down to minor gods, and also you get a little multicultural here, and you start to name minor objects in the solar system after Mayan objects or Hindu deities or Buddhist entities and so on. So it's kind of interesting how the naming goes. The governing body of all of this is the International Astronomical Union, which also sets a rule where you can't just name an object after yourself if you discover it. That just doesn't happen. And if you see ads on TV or on the internet to buy the rights to name something, a constellation or a star or an exoplanet after yourself, you can pay the money to do that if you like and get a nice certificate to put on your wall, but it has no validity with the astronomy community.
The next question is from Mihek, who's on with us live, who would like to know, is quantum immortality possible?
I'm not sure quite what the concept means, but it could relate to a question of whether living forever is made possible or enabled by our deep knowledge of the quantum world, the subatomic world. The short answer is no. There's no reason to believe that immortality is possible because we know enough about biology to know that senescence, which is the word for the sort of termination of living organisms, is built into all living organisms. That's just a part of biology. All living things die. There are some interesting creatures that, simple creatures that sort of regenerate cyclically, but they don't live forever. The governing fact of this for larger creatures, animals essentially, is the fact that the DNA end caps, called telomeres, degrade over time. And the finite degradation of a telomere means that the DNA is degraded. And so the cells, lose the ability to function, and that makes the cells vulnerable to cancers or just to cell death. There's a thing called the Hayflick limit, which is the practical number of times any cell can subdivide. I think it's 47 is the number. It's not a perfect number. It varies depending on the species. So mortality is essentially built into biology as far as we understand it for all creatures. And circumventing that, or even slowing that down, is a challenge that scientists have accepted. Does our knowledge of the quantum world and how subatomic particles work get us any further down the road? No, because even knowledge of the subatomic world and quantum mechanics doesn't mitigate the fact of biology, where complex systems essentially have, date stamps put on them so that they eventually terminate.
The next question is from Terrence, who's on with us live. Professor, oxygen is toxic to humans at extreme depths in the ocean. Is the same true in outer space? Like, is oxygen toxic to astronauts?
The level of oxygen that is safe for humans is quite narrowly defined. Now, this is true of all large animals and mammals especially. The oxygen content of the Earth's atmosphere is about 18%, or most of the rest is nitrogen, which is an inert buffer gas and doesn't really react biologically much at all. If that oxygen level goes down by a factor of 2, then essentially a human or a mammal or an animal will asphyxiate. It's just not enough oxygen to maintain cell function. If the oxygen goes too high, a different thing happens, because oxygen, of course, is highly corrosive. It's a highly reactive gas. And so at too high concentration, the cell metabolism cannot keep up with this highly reactive gas, which will oxidize things in the cell that shouldn't be oxidized and essentially destroy cell function. So there's a sweet spot. When divers get the bends, that's because they're being given that's because they need oxygen underwater. They're breathing artificial combination of gas. And as you change the depth and the pressure, the nucleation of bubbles in the oxygen changes. And those oxygen bubbles can nucleate inside the body. And then the oxygen is not being used in the normal way. And that's a very terrible and often fatal thing. And so again, you need a buffering gas to stop that from happening. And of course, you need to raise the pressure as a diver comes up very slowly. But there definitely is a optimum level of oxygen. Also, if the oxygen content of the Earth's atmosphere was above about 30%, I think the historical high 300 or 400 million years ago was over 30%. But if it goes up to about 35%, the atmosphere could literally combust.
The next question is from Dave McKenzie, who sent an email. Are there telescopes that are completely dedicated to observing Betelgeuse to possibly witness a supernova from start to finish? Is it close enough that we feel like we should dedicate an entire instrument to it?
I think that is happening in an informal way. No major telescope is doing this, of course, because Betelgeuse is a bright star. It's a naked eye visible star. You don't need a large telescope to study it or to get the hint that it might be about to go off. So monitoring with a small telescope is perfectly adequate. And there are hundreds of small telescopes in the hands of amateur astronomers that are wanting to do research and contribute to the field of astronomy. And so that's why there's so many of these telescopes that I can't say exactly how many or who may be monitoring Betelgeuse, but I can guarantee that several of these telescopes, and perhaps some of the robotic ones that the professional astronomers use, they're also small, are routinely observing Betelgeuse. Maybe not all the time when it's visible, but certainly every night or maybe several times a night while moving around other targets. So yes, there's sufficient attention being given to Betelgeuse that we will get a heads up if it's about to go off.
All right, thank you very much. The next question is from Wendy Traver, who sent an email. I read an article that said that symmetry breaking and entropy are responsible for creating the diversity and richness of the universe as it presently exists. Can you talk a little bit more about this interesting idea?
Well, there's a very profound way in which symmetry breaking creates an interesting universe, which is the fact that if the particle-antiparticle symmetry were perfect in the early universe, then in the early universe, all the particles and antiparticles that were being created out of pure radiation, pure energy, in equal numbers would have annihilated to make more energy. And so the universe would essentially just be filled with photons. Those would degrade in energy as the universe got older and bigger, but that's all there would be. And so there would literally be no matter, no structure, no planets, no stars, no galaxies, no life. So that's the most profound example of where symmetry breaking, this slight asymmetry in the creation of particles and antiparticles makes for an interesting universe.
The next question is from Penny, who asks, why can't we see beyond the observable universe? Why is this observable universe actually the observable universe? And why are those limits?
It's a simple function of the fact that the universe has a finite age. We don't know if the physical universe is infinite or not. We simply don't know. It could be. We know we live in an expanding universe, however, and we know the time since the expansion started. It's about 13.8 billion years. And that finite age of the universe means there is a maximum distance that we can see where light could reach us in 13.8 billion years. And that essentially defines the edge of the observable universe. And in that sense, the observable universe gets bigger every day as light from slightly further and further regions reaches us. But it is a fundamental limit associated with the finite speed of light.
The next question is from Don Town. I'm not sure if you're familiar with this project, but there's a project called Reflect Orbital where they want to launch mirrors into space or into the upper atmosphere to be able to reflect sunlight down and basically have sunlight on demand. Don Town would like to know if you think that such a project will get approval and if you think it's a good idea or how people like average citizens might dissuade the government from giving approval to a project like that if it would indeed be harmful to astronomy or to us on the ground.
Right. This project, and there are others that are similar to it from the private sector, so non-government funded, is an attempt to, harness energy and deliver energy and make an economic model based on energy delivery from space. So you're harnessing solar power, you're focusing it, and then beaming it down to the Earth. Sometimes you're converting it into microwaves to beam it down to the Earth, and then, of course, it's heating up material or driving turbines or doing all the things that energy can do to be transmitted to the people who need to use it. Putting large numbers of mirrors in Earth orbit is a very unpopular idea, of course, with astronomers because these mirrors, of course, are reflecting solar radiation, but also all the other lights that are out there. And the near Earth orbit is a kind of a busy place. There are satellites that have lights on them. The International Space Station, of course, is flooded with lights from the inside. So near Earth orbit is not a totally dark place. And so when you put all these mirrors up there gathering radiation, they're not going to perfectly beam it down to one location. There's going to be leakage, there's going to be scattered light, and yes, that's going to make astronomers' lives much more difficult. So these are kind of unpopular ideas. On the other hand, I don't think any of them is economically feasible at the moment. So the capital cost of launching enough large mirrors into orbit and developing the technology to steer that reflected solar radiation to the location where it's needed and convert it into useful energy, the capital cost of that is very high, and the economic model I don't think is very well developed. So these are projects that may never come to fruition, and even the practical planning of them is going to take 5, 6, maybe 10 years.
The next question is from David Gold. Does Aristotle's prime mover concept apply in any way to the field of astronomy today?
Well, Aristotle, was a deist in the sense that he believed that the universe had an overall governing divine force, that was something we might call God. And so the prime mover was just his term for an entity, a supernatural entity, if you like, that animated the spheres, that animated the motions of the cosmos. He did not believe the Earth was moving, so he thought that all the planets and the sun and the moon were on crystalline spheres that orbited the Earth. And then there was a question as why were they orbiting and what caused that motion? So he invented the concept of the prime mover. Again, we would call it God in modern terminology to explain that. So in the sense that there are some theists or deists or people who believe in God who attribute God to God, the power to animate the universe, then yes, that idea is still in play. But it's a very archaic concept in the hands of Aristotle going back over 2,000 years.
The next question is from Robert Petrillo, who sent an email. Could you explain how modern radio telescopes mitigate radio frequency interference from human technology, and what technological skills, such as signal processing, antenna engineering, array calibration, are most in demand for the next generation of radio instruments?
Sure. The way radio telescopes operate in a noisy radio terrestrial environment, because it is, we can think of how many hundreds of radio stations there are, and shortwave radios, not just commercial radios, and microwave transmitters of various kinds. So across all parts of the radio spectrum, from millimeters to centimeters to meter length radio waves, there's stuff going on out there. The way radio telescopes navigate this noisy terrain is through looking for narrowband signals. And so basically you have a spectrum analyzer behind your radio telescope that is chopping up the signal or distributing it into small or narrow frequency channels, maybe only 1 hertz wide. And then in some of those channels, many of those channels, there are no artificial sources of radio information. Radio transmitters tend to be broad spectrum, but they have certain allowed channels. There's an international and a national governing body that says what parts of the radio spectrum are available to commercial entities and what parts are protected for astronomy. And so astronomers have been protected to have their own quiet zones of the radio spectrum for over half a century. There's been problems with that, compromises, or just buccaneer outfits that just put their radio transmitters in protected parts of the spectrum without permission, and then they have to be hunted down and told not to do that. So preserving the quiet radio sky has been a constant battle, and it's getting worse, I would say. But the good news is that those protected zones for radio telescopes are still holding more or less.
The next question is from an email. Shouldn't SETI and other researchers be exploring post-biological civilizations as a way to answer the Fermi paradox?
Yes, I would say SETI researchers are taking a broad view of their subject now. They're not simply looking for pulsed radio and optical signals in the traditional mode of SETI for over half a century. Astronomers involved in SETI are well aware that post-biological evolution could lead to a universe filled not with biological entities like us, but could be filled with robots or AIs or computer intelligence of some kind. And recognizing that becomes difficult. So that's the real problem with it, broadening the scope of SETI to include post-biological evolution. We don't really know what it's going to look like. How do you detect an AI in general, especially not one that we use? AI is a fairly recent phenomenon on the Earth. But if AI has been around in the universe for thousands or millions of years, what would that even look like? And so the detection problem is not really a detection problem, it's a recognition problem. And I don't think anyone's really resolved that.
The next question is from one of our live participants. Since we see stars twinkle, we know the density of the atmosphere affects the starlight, but does the gravity of the Earth affect it at all?
Well, according to general relativity, mass bends light. So the modest mass of the Earth, in principle, is causing a very slight gravitational deflection of light that comes in from the universe, or light that crosses the Earth or is anywhere near the Earth. But for an object the mass of the Earth, that space-time curvature and that bending of light is so tiny that it essentially can't be detected. General relativity was confirmed by looking at the gravitational deflection of the Sun, which is 1,000,000 times more massive than the Earth. So you can tell that the gravitational influence of the Earth on light is extremely small.
The next question is, I'm going to make it a little bit more general, but what are your perspectives on the current political situation in the United States as a scientist and teacher?
Well, we're suffering a double threat at the moment in academia, as a scientist working in academia, as I am, and many of my colleagues. The first part of the threat is the threat to federal funding of science research, and that's been ongoing for months. The DOGE cuts that came were heavy cuts to most of the science funding, not just of the National Science Foundation and NASA, but the National Institutes of Health, Cancer Research, all the entities, Department of Energy, all the entities that are doing science research. The bottom line on those cuts is not known yet for the next fiscal year, because the president's budget has proposed deep cuts to NASA and the NSF, about 50% to their science funding. But Congress has not agreed to that, and actually Congress has pushed back gently, and the final appropriations will not happen for another month or so. So the worst of those cuts may not happen, but the best we could even hope for is flat funding. And that in real terms means science has lost ground, because there have been cuts in the last decade, and science is expensive and inflation is not being accommodated. So the science power of the federal budget is lower now than it was at any time in the last 25 years. That's one aspect. From the university aspect, it's a new thing and it's more ominous. My university, University of Arizona, was one of 9 universities singled out by the Trump administration to sign a compact, as it was called, where in return for preferential treatment in federal funding in the future, we would give up some autonomy, suffer implications to our academic freedom, to micromanagement of our enrollments, the inability to raise tuition would be capped for 5 years, or a whole set of requirements. I'm glad to say that our university just a few days ago, because the deadline was the 20th, declined to sign the compact, although our president equivocated somewhat. He tried to thread the needle. MIT strongly rejected the compact, and I think the University of Virginia is the only one, and the University of Texas are the only 2 of those first 9 that have said they want to work with the compact. But the compact, make no mistake, it represents a severe threat to the autonomy of universities. So essentially, this administration is using their power of the purse and the fact that the federal funding does come from the government, which means, of course, in the end from the taxpayer, and he's holding it over the heads of all the universities to get them to do what is essentially their political bidding. It's a very uncomfortable situation.
The next question is from Eric, who's on with us live. Why are we, or why does it seem like we are seeing more out of the solar system comets or objects? Why are we seeing more objects that seem like they're coming from outside of our solar system?
Yeah, it's not just a perception. It's true. The number is still small. The absolute number is small. It's less than half a dozen, I think. But it's more than a handful. And there was a long time when we didn't know of any interstellar interlopers through our solar system. Oumuamua was the first and most prominent 5, 6, 7 years ago. So why are we seeing more of these objects? It's because we're monitoring the sky better. We have now networks of telescopes. They are modest-sized telescopes, and they are monitoring the skies routinely, and they're looking for near-Earth objects. Some of this work involves tracking objects that might potentially collide with the Earth and cause a devastating mass extinction. So that's protecting the planet from near-Earth objects that could collide with the Earth. But those same surveys find any kind of fast-moving object that's not on a standard circular or elliptical orbit in the solar system. And the interstellar interlopers really stand out because they're moving extremely fast. They have speeds that can carry them between stars. So their speeds are obviously higher than the escape velocity of a typical star system. And they're moving on sort of hyperbolic or parabolic trajectories, and they come and go very quickly. So if you don't study them quickly, you lose them because they're not in captive orbits in the solar system. So once they're gone forever. So we only get a little data on them. But yes, because of our increased powers to monitor the sky, people are setting alerts for anything that moves fast and looks like it has orbital elements that suggest it's an interstellar object.
The next question comes from one of our live participants. Dennis asks, can you describe the recent evidence that suggests life may exist on Venus?
I think there's no good evidence that life exists on Venus. Venus, to recall, is a close twin of the Earth, really, within 4% of the Earth's mass. It's closer to the sun, 30% closer to the sun, so it gets, substantially more solar energy. But that alone is not enough to explain its incredibly high temperature, something like 700 degrees Fahrenheit at the surface, hot enough to melt lead. That's explained by the fact that it's an extremely active volcanic planet that has been generating huge amounts of carbon dioxide through volcanism over time that has led to a runaway greenhouse effect. Venus, for example, had an enormous episode of global volcanism about 700 million years ago. So the Venusian atmosphere has had a runaway greenhouse effect that's made it extremely hot. Because of all the volcanism, there are a lot of toxic gases in the Venusian atmosphere. And so most people don't really think it's very habitable. There's no place we know of where there could be liquid water in Venus, except perhaps deep underground, under pressure. So when people observe things like phosphine in Venus, which has been observed in very trace quantities on Earth, phosphine is a chemical that is associated with biology, but at this low level that has been seen in Venus, it does not necessarily indicate life. There are abiotic or independent of biology mechanisms where phosphine at a very low level, parts per billion, can be created. So I don't think there's any good or interesting or compelling evidence for life on Venus, and I would be very surprised to see some.
Excellent. Thank you very much. The next question is from Adi, who asks, what are your thoughts on the recent discovery about two colliding black holes? It's fairly general. I know that there have been several detections, but perhaps you can talk about some of these, what we've learned about colliding black.
Well, the most that we've learned about colliding black holes has been from the extraordinary success of the LIGO project, the Laser Interferometer Gravitational Wave Observatory, two huge instruments with 5-kilometer orthogonal arms situated in Washington State and Louisiana State in the United States, operating in tandem as to detect synchronous pulses against various contaminating noises like geological noise. LIGO was built essentially to detect black hole mergers or neutron star mergers or neutron star black hole mergers, and it's been enormously successful in that task. I think over now 100 events firmly detected by LIGO, most of which are black hole pair mergers. So we've seen a number of these. The more surprising results recently in the last few months have been that some of these black hole mergers involve very massive objects of a few dozen solar masses. And that's beyond the level of the black holes we expect to result from the death of a massive star. So the sort of anomalously high masses of some of these black holes, which are essentially dead stars, is rather confusing to some people because the stellar evolution models don't really say it should be very rare to get black holes more than, say, 20 or 25 times the mass of the sun. You'd have to have a star that may have been 150 or 200 times the mass of the sun die to get a black hole that massive. And most people think stars that massive, they collapse so violently that they blow themselves apart and don't ever create a physical object like a black hole. So I think that's the surprising information that's coming out of LIGO on black hole mergers.
The next question is from one of our live participants. Birhane asks, why does the blood moon happen and what effect does it have on Earth's environment?
When the blood moon happens when the moon is seen through a dusty region of the Earth's atmosphere, and it's when it's low in the sky especially. There's also a sort of refraction happening, which moves the blue light away. The blue light is the reflected blue light from the moon is absorbed or scattered by the Earth's atmosphere, and it leaves the red light untouched. So the moon looks blood red, especially down near the horizon. So it's just a phenomenon. There's nothing special about that. It's a phenomenon of the orbit of the moon. And when the blood moon is large, when the moon happens to be closer to the Earth, because the Earth-moon distance varies by about 10% over the orbit, then of course it's a very prominent object and people tend to notice it.
The next question is from Arif Roni. The concept of symmetry in physics and symmetry in biology, are these somehow connected?
Well, a little bit. And the symmetry that's part of physics is really associated with fundamental physics, like the nature of the forces, and the symmetry between particles and antiparticles, which comes out of quantum theory. So it's a very profound and basic and fundamental level of symmetry. Symmetry principles in biology arise somewhat differently, and they really come from the handedness of biological molecules. So a lot of biological molecules have a helicity or a handedness. You can think of them as a left-handed glove and a right-handed glove, but it's a molecule. It's called chirality in biological terminology. So many molecules in biology, including, of course, archetypal RNA and DNA, have a helicity or a spiral structure, and proteins do, and many biological ingredients do. And in the case where there is possibility of two equal handedness, left-handed gloves and right-handed gloves, only we're talking about molecules, you might expect to see equal numbers of each, but you don't. You see one helicity or handedness dominates biology. So there's a symmetry broken there between those two equal shapes, just like mirror images of each other. The reason for that asymmetry is fairly clear, because biology needs to be efficient in its use of energy, and it's an inefficiency for biological interactions and biological mechanisms and biochemistry to have to double its number of reactions by working with the left-handed and the right-handed molecules separately. So it's logical that in the evolution of life on Earth, biology would have chosen, that's a very anthropocentric word, so I'm using it cautiously, one of the handedness molecules over the other, and therefore you end up with a chirality of life that represents an asymmetry.
The next question comes from one of our live participants. As time is always relative and will be the same for each individual, and it can be slowed down, some of those, seem like assumptions. Is it possible by any chance to go back in time?
We don't think so. It's an interesting question just because fundamental physics has a strong time symmetry. The most profound symmetry principle in physics involves the combination of charge, that's electrical charge, positive or negative, parity, which is the spin of a particle, even if they're not physically spinning like a top, they have an implicit quantum spin, one direction or the other, and time, the arrow of time. And at the level of fundamental particle interactions in quantum theory, particle interactions go equally well and are equally facilitated going forward and backward in time. So fundamental particle physics has no time asymmetry and essentially knows no arrow of time. The arrow of time, and the fact that in the macroscopic world that we live in, time flows in one direction, is a function of large number of atoms and molecules. And that's where we think the origination of the idea of entropy in thermodynamics and the arrow of time derives from. But that's not a fundamental physical principle. That's a sort of statistical principle, statistical mechanics essentially applied to complex systems. Does that mean that macroscopic large objects cannot have their time arrow reversed? We haven't found any particular way to do so. So the fact that at the fundamental level of subatomic particles, time is symmetric doesn't really help when you're dealing with a complex organism like a person. So I don't think a person or even a single cell can have their biology or their clock run in reverse. Nobody's ever thought of any conceivable way to do that.
So another similar question, is it possible to see past events that have happened on Earth by capturing the light that got reflected from it? So could we use light as a way of sort of seeing back in time on Earth?
In principle, yes, that's an interesting idea. That the fact that there's a history that whatever's happened on the Earth, the information about that is going out in space. And if it were somehow reflected, just imagine an advanced civilization set up huge mirrors in space. And if they were 1,000 light years away, those mirrors would be telling us, when we looked in the mirror, of things that happened on Earth around the time of Christ, 2,000 years ago. And if that civilization in that large mirror was 10,000 light years away, we'd be looking at things that happened on the Earth at the dawn of fixed civilizations 20,000 years ago. So yes, as a thought experiment, it's entirely possible that ancient light from the Earth could somehow make its way back there. It's not going to happen naturally, however. It would happen in an unnatural way, like the one I described.
The next question is from Arif Roni, who's on with us live. And the specific question is, dimensionless constants, like coupling constants, do they tell us something about the complexity of advanced physics? Are there more dimensionless constants in advanced physics? So can you talk a little bit about dimensionless constants and what do they show us and teach us about the universe?
Right. So, the fundamental physical quantities in the universe are mass, length, and time. So it's common in physics, going back to undergraduate classes, that you work with quantities that could involve force or pressure or electric charge, anything. And in the end, they're reducible to these three elements of mass, length, and time. And we have our own units for these things of kilograms, seconds, and meters. However, you can make combinations, you can make dimensionless combinations of these quantities, and that's what these dimensionless constants, like the fine structure constant, are. And there are really only three of them in fundamental physics. Are those universal? We think so. There have been astronomy experiments to actually look at whether the fine structure constant in particular, which affects nuclear physics, atomic physics, is different in different parts of the universe in terms of how interactions work. You can probe whether the fine structure constant is different far from the Earth, looking back in time, or in this part of the universe versus another part. No one's ever found an instance of the fine structure constant varying anywhere. So we think it's a fundamental universal constant that's built into physics and that every part of the universe has to obey, and every civilization that was understanding physics would understand the same thing. There's no fundamental limit on how many dimensionless constants you can conjure up out of the basic mass units, but there are several that seem to be central to physics.
The next question is from, Carol Miklas, who sent an email. I'd like to understand more about dark matter. Could you explain its importance in astronomy, how it's measured, and do you have any book or reading recommendations on the subject to learn more deeply?
Yeah, the dark matter is profoundly important because the normal stuff that we're made of, protons, neutrons, and electrons, and normal matter, if you add up all the atoms we're made of on the Earth and all the planets and all the stars and all the galaxies, few hundred billion of them, it only amounts to about 4% of the material universe, mass and energy. Most of the rest, 2/3 of it, is dark energy, that we don't understand at all. But about a quarter is dark matter. And so dark matter outweighs normal matter by a factor of about 6. And we don't know what it is. So it's a pretty big problem to have identified, all these atoms that are composed of physical matter in stars and galaxies, and yet know that they are all outweighed by a factor of 6 by something that we don't know what it is. We do think that it is a fundamental particle, as yet undiscovered, as yet undetected in the lab, but experiments are underway to try and detect it. But we don't know. So until we find it, we simply don't know. But dark matter has a profound effect on the universe because, of course, the cosmic expansion is mitigated or modulated by dark matter, which is an attractive force slowing down the cosmic expansion. And so if there were no dark matter, the universe would be expanding much faster than it currently is. So dark matter has an effect not only of holding galaxies together, because the stars in them would fly apart if dark matter didn't exist, but also of changing the arc of cosmic history.
Excellent. Thank you very much. The next question is from Svetlana. Are you familiar with Comet Atlas? And if so, can you tell us a little bit more about the Comet Atlas and sort of its, future?
Yeah. So Comet 3I Atlas, I think is its full designation, has been tracked and monitored. There are nice animations you can find online showing it moving across a star field. So it's a rapidly moving object. It appears to be an interstellar comet, one again of a handful of these objects that have been found in the last few years. And it's being very heavily scrutinized because we know, given its trajectory and its orbital elements, that it won't be visible or stay in our solar system for very long. As to its physical nature, its size, its composition, I don't think at the moment we know. But people are working on it, and some pretty big telescopes are studying it right now. So I suspect we'll learn a significant amount more about it before it departs the solar system.
The next question is from Storyblocks. After the terraforming of Mars, can humans live on the planet? So can you talk a little bit about what it would take to terraform Mars, and is it ever possible that we could live on it after terraforming?
I think terraforming is an incredibly difficult, time-consuming, and expensive thing, but it's not impossible. It doesn't break any laws of physics. It's just a practical problem in a sense. Terraforming means taking a planet that's barely habitable, that has essentially no atmosphere, that has gravity 40% of the Earth, and giving it a breathable atmosphere such that life can exist there. And that would actually be a three-stage process. So we know what the stages are. First of all, you have to warm up the planet, which is a way of liberating not only some of the frozen water that's under there, but a lot of the carbon dioxide in the planet to create a greenhouse effect. So that's the first step. And you'd have to warm up the planet by about 15 to 20 degrees C over the whole planet to liberate both water and carbon dioxide. And then you start a greenhouse effect. That feeds on itself because it's a positive feedback loop. So the positive greenhouse effect would continue to warm the planet. Then you seed the surface with microbes that are able to exist. So the first stage of life is extremophiles that can exist in what is still a very challenging environment that has no oxygen yet. You're trying to establish microbial colonies and to get life with a foothold and get ecosystems of microbes there. And some of those microbes could be used to liberate oxygen, photosynthetic microbes, of course. And so in that third stage, you migrate the biological seeding of the planet to microbes that are feeding oxygen into the atmosphere, thickening the atmosphere with oxygen. And the atmosphere would need a buffer gas, just as the Earth has 80% nitrogen. Mars would need a buffer gas too. So you'd have to somehow put a neutral buffer gas like nitrogen in there. And that's not clear how we would do that. So that third stage of oxygenating the atmosphere, that's going to take a long time. Nobody really knows how long. So all of these three steps are possible. They involve enormous amounts of energy. They're obviously very expensive to do. They're not technologically impossible, but they're challenging. And if you had to put numbers on it, then the ballpark for terraforming Mars, if it really is possible, is trillions of dollars, not billions, but trillions of dollars, and hundreds of years. So this is not a project that anyone would undertake lightly. It's far more likely that we'll go to Mars in limited places. We'll set up little colonies or research stations under bubble domes and perhaps terraform patches of Mars to be able to survive and grow crops and live under domes, if you like, but not the whole planet.
Excellent. Thank you very much. I'm going to quickly, for those of you who are still here, remind you to like and subscribe. So hit the thumbs up on this live session video so that we can get the word out to more people. Make sure you subscribe to our channel. And we are going to take one final question. Actually, there's two questions. We're going to wrap up with these two, but these are related questions, and I think we can cover both of them. The first one will be, are the signals from Voyager 1 and Voyager 2 still being received and understandable?
Yes, I think so. There was a loss of signal from one of the Voyagers. I can't remember which one. And the transmitter power on those spacecraft, after so long, they're powered by radioactive elements, and that's why they've lasted for over half a century. No normal power source could possibly last that long, except a radioactive one. Their transmission power is a fraction of a watt now, radio power. And that's still amazingly detectable from the Earth. So yes, we are still tracking, I'm sure one and possibly still both of those spacecraft at distances of about 18 to 20 billion miles from the Earth.
And the final question for today is, will Voyager 2, from John M., will Voyager 2 ever be able to reach another star system, or will it disintegrate in the tens or hundreds or more years it may take to reach another star?
Actually, the time to reach another star, to go far enough to be in the realm of another star, is more like tens of thousands of years. They're moving quite slowly, so remember, it took them almost a decade to leave the solar system. Distances between stars are tens of thousands of times more than the size of the solar system, so you multiply that up and you get a long time to reach a solar system. And also the trajectory of all the 5 objects that left the solar system do not take them in the direction of a nearby star. It just doesn't happen to be the case. They were never aimed that way anyway. So these are not spacecraft, Voyager 2 or the others, that are going to end up near a star in any kind of a millennial timeline. They're messages in a bottle that have been thrown out into the voids of space. The spacecrafts, however, will endure. They're built very sturdily to survive, intense geomagnetic fields in the Jovian system, cosmic rays, and so on, and they're tough. So the spacecraft are not going to be destroyed by traveling through interstellar space for eons. Those are interesting questions today, as usual, from everyone online and live. Thank you. And Matthew and I will put our heads together and map out the next few sessions soon. Thanks to him for facilitating, and we'll be with you in a couple of weeks.
All right. Thank you, everyone. Again, hit that thumbs up on the video, and we will talk to you in just a couple weeks. Thanks. Take care, everyone.